Hello, everyone. Thank you for being with us today, this afternoon, for our weekly webinar of the series Conversations with Mexicans in New England. The series is organized with the help of our wide network of Mexican scientists, artists, entrepreneurs, researchers, and educators living in New England to help us bring awareness to the important contributions our community is making in the United States to science, literature, academia, and innovation. Today, we have two very important guests, Luis Adolfo Orozco and Daley Ornelas, who will be talking with us about quantum physics. So we have much to learn. Dr. Luis Adolfo Orozco was born in Guadalajara in 1958. He studied engineering at the Instituto Tecnológico de Estudios Superiores de Occidente, ITESO as it's known. And he did a postgraduate at the University of Texas, obtaining a doctoral degree in 1987. He completed a postdoctoral stay at Harvard University. He worked from 1991 to 2003 as professor in the physics department of the State University of New York at Stony Brook. As of 2003, he is professor of physics at the University of Maryland in College Park, Maryland, where he was co-director of the Physics Frontier Center of the Joint Quantum Institute between 2008 and 2019. Throughout his career, Dr. Orozco has been a Guggenheim Fellow, Fellow of the American Physical Society, Fellow of the Optical Society of America, Fellow of the Institute of Physics in the UK, Distinguished Traveling Lecturer of the American Physical Society, and member of the Mexican Academy of Science since 2005. And he's been traveling very much to China, following up all the students he has been teaching and helping graduate for years. Daley Ornelas was born in Aguascalientes in 1989. She has a degree in physics from the Universidad de Guanajuato, where her thesis work on the characterization of microstructured photonic fibers was awarded. Subsequently, she completed her Ph.D. in physics at the University of Maryland in College Park under the supervision of Dr. Trey Porto and Dr. Stephen Ralston. Her doctoral thesis was devoted to the study of the interactions between ultra-cold photons and atoms. We will hear more about this, won't we? During her graduate studies, she received the Monroe H. Martin Graduate Research Fellowship and the Graduate School Dean's Fellowship. She has served as scientific advisor for the Foro Consultivo Científico y Tecnológico of Mexico, and she has also been a mentor in science outreach projects such as Clubes de Ciencia México and America Reads, America Counts. Thank you so much, Dalia and Luis, for accepting to be with us today for this conversation.
Thank you for the invitation.
My pleasure, my pleasure.
Yeah, so let's start chatting after all your bios been read. Luis, can you please tell us a little more about your trajectory and your experience while studying abroad? Why did you decide to study quantum physics? How was your postdoc here in Harvard?
Look, I am a great believer that life is a random walk, that there is no purpose in life, and that things happen, stuff happens, and yes, I ended up studying physics, right? So I finished engineering in Mexico, and then got the possibility to study at the University of Texas in Austin, where they awarded me a teaching assistantship. So for the first couple of years, I was a teaching assistant. And by the way, I still keep contact with some of my first from the teaching assistantship. And then after I finished there, the opportunity to join the group that was attempting to measure the mass of the antiproton at CERN, but it was a professor at Harvard, Jerry Gabriels, arose, and so I joined. Again, why did it arose? Because of a random walk, right? So just stuff happens and you grab it and you continue. For my PhD, I indeed did doctorate. My doctorate was in quantum optics, right? So that was my first real, let's say, facing with quantum physics, right? So I think everybody who is a physicist studies quantum physics, whether you dedicate the rest of your life to quantum physics or not is a different issue. My years in Harvard are probably some of the most wonderful time that I've spent in the US in my life, in New England. So this is very, very nice to me to be talking with you about that. In those days, I did meet the consul. He was an architect, and I don't remember right now his family name, but no, Bonilla or something like that. Anyway, but but what did I decide to study quantum optics? It seemed to me, again, that I was in a random walk, not knowing what I wanted to study. And this possibility arose and I grabbed it, and that was it. But I don't believe I had a plan. Okay, I can create a narrative that tells you that I knew what I was going to do, but that's not true. That's really not true.
And I agree with you, Luis, that rarely someone, maybe if you're a lawyer or a doctor and your father and your grandfather were lawyers and doctors, but the rest of and you decide to follow that career, maybe. But most of us, it's true, life takes you through different paths, and one choice will be taking you to the other. Before we go to Dalia, tell us a little bit about the program you supported with the Sociedad Mexicana de Física that has helped over 30 Mexican undergraduate students to spend 10 weeks of summer doing research in Maryland. How did this program happen?
Sure. Yeah. Look, let me start by saying that I think that's the proudest thing the one thing I am proud of having done. Okay, the rest is irrelevant, but this really I am very, very, very proud of. If I am held accountable, that would be the credit I have in my bank. Okay? So it started exactly 25 years ago. Okay, wow. I was invited to give a plenary talk at the annual meeting of the Sociedad Mexicana de Física in 1995. We had recently succeeded in an experiment with francium, and they wanted to hear about it. And the meeting was in Zacatecas. So I went there, and while staying there, I started to talk basically with one professor of physics at CIMESTAF, Miguel Ángel Pérez Angón, and I said to him, hey, is there a possibility that you could send me some students in the summer? So this was just between him and me, and he, who is a very, very go-for person, said, let's try. And so he was a member of the particle physics community in Mexico. He's still a member in CIMESTAF, which helped start the program because the high energy physics community had the connections with the big accelerators, both in the US and in Europe to send students. So he said, well, look, we can figure out how to do that. And for the first year, which was in the summer of '96, was when the first two students arrived. Between him and I figure out how to find the money for the airplanes and how to find the money for the housing here. And they spent 10 weeks. That was in New York, while I was at Stony Brook. And the program then got a little bit more and more institutionalized. Then in the first 6 or 7 years, it was the particle and field community in high energy physics in Mexico that organized it. And then it got eventually moved to the part which is in quantum information of the Mexican Physical Society. Now, why was I interested in this? I thought that one of the big, very, very pleasant surprises I had in my learning was to be able to do experiments with real resources, And I saw that in most cases, in Mexico, there was on the one side still a very heavily loaded thought that physics was a theoretical science, and that playing for experiment was done by technicians, not by the scientists. You didn't get your hands dirty. And I thought that that was not very good. And here is where I learned, yes, you get your hands dirty and you go to the lathe, and Dalia can tell you a lot about getting your hands dirty, right, Dalia? And so a little bit about that triggered me for the interest. And I saw by that year, I had been 5 years in Stony Brook, I had undergraduates coming to my lab and working and growing on in their understanding of physics. So that was what, and then at some point, the U.S. Mexican Foundation, or the Mexican-U.S. Foundation in Mexico, supported it. So over the years, different sources paid for the bills. And eventually we got into something that the Mexican Physical Society will figure out how to deliver the students in the United States, and then I would take care of. And that's, and I didn't have anything to do with the choice of students. So I met Dalia when I remember that you had to take you arrived in Baltimore, right?
Yeah.
Yes. You arrived in Baltimore. So that's what, after that, then we met. Okay, so that was the plan. And I think now there are more than 30. And of those 30, more than half have finished their PhD, and at least 8 have started research groups in Mexico.
Wow. So that's kind of like the Indian model, no? Many Indian professors do that with Indian students, and I think Chinese too. But unfortunately, in Mexico, there's not as many people doing what you are doing. So congratulations.
Well, look, let me just take exception. This is done with undergraduates. I wasn't doing it with graduate students.
Okay. Mm-hmm.
The Chinese and the Indians do it with graduate students.
Okay.
So it was a much more complicated from the how do you get the visas to come and so on, but people always helped and figure a way, because these were undergraduates.
Okay.
They were at the end of their 3rd year.
Okay.
That's the perfect timing.
Great. For learning a lot in labs. Yeah.
No, for opening your eyes and seeing that you can have fun in a lab. Yeah. And I guess Dalia can now take over from the other side.
Dalia, if you were part of that program, but first tell us what made you from Aguascalientes decide to study in Guanajuato? It's not far away, but it's 2 states away, and physics. And then tell us about this program. How was your experience? How was it useful, and how did it affect your life?
Well, I think, as a lot of scientists can tell you, like, since you were like very young, were very curious about nature, you know, the universal Carl Sagan series. So I knew that I wanted to do science and physics, but there was no major in physics in Aguascalientes, so I had to go to the next nearest university. And originally I wanted San Luis, but my mom said, like, no, the highway from Aguascalientes to San Luis is horrible, so you're not going to San Luis. Like, okay, well. Then the next one was Guanajuato. The Physics Institute was in León, so I did my undergrad.
Good highway between León and
it was better.
Aguascalientes for sure, yes.
Yeah, it was better. I mean, some part of that highway from San Luis and Aguascalientes is very scary, so I can understand my mom. But anyways, so then at the beginning, I wanted to do theoretical physics because it was like the strong sort of research area, like cosmology and gravitational physics. But then before going to the summer internship with Luis, I did some experimental internship at UNAM in solar cells. And I really like it. And I thought, well, you know, experimental physics is like more applied. You can see it more in real time, like the results. So I really enjoy that. And then there was this opportunity of, well, it was like, I mean, not a competition for, sorry, I forgot the word, to do this summer internship with Luis. So I applied. So there were some professors that interviewed me, and they decided that I was I was okay to go and work with Luis for a summer, 10 weeks, I think, or 8 weeks, I believe. And I mean, it was great because you go to the US and you see the amount of resources that unfortunately in Mexico you just don't see for experimental science. It's difficult to do experiments in Mexico, unfortunately. And you know, people from other parts of the world, and just you know, very brilliant people. And it really opens a new door for you, like these kind of experiences. Before this summer internship, I really didn't even know that you could do a PhD in the United States. Like, I was planning to continue in my small university. And then after this, you know, I learned that, well, you could actually go abroad and do a PhD. And here I am. Now I'm done.
And now you're in Boston.
And now I'm in Boston.
That's why we're having this conversation. So but I understand that you just arrived here because precisely Boston is a very important area of innovation, but you will have to be looking for your way, and hopefully very soon you will find interesting projects over here.
Yeah, that's the hope.
Now, let's go to quantum physics. It's not an easy topic to understand. I understood a little bit more with your video, Dalia, today. Thank you for sharing it. But so we would love to hear more about your research. Could you try to explain us in a simple way, as you do with your video, what is quantum physics? What is its purpose and applications? And this is for both of you, but Dalia, maybe you begin.
Oh man, it's just quantum physics is like a really, really broad area. This is very difficult. So quantum physics is the area of physics that study nature in its smallest scales, because when you go to that small scale, like just nature behaves very differently to how we usually know our world. So all the rules that we know change, and everything, it's not intuitive. And why is it important? Because, you know, the atoms are, you know, the building blocks of matter. So it is important to know how to understand like these building blocks, right? And in doing so, we can make also some technological developments. And by now, for example, the hope is to have at some point quantum technologies like quantum computing or quantum communications. And this is my very broad explanation, but probably Luis can do it.
No, very good. So look, I completely agree with what Dalia has said. To me, there are probably the most important scientific idea that we have to preserve is that everything is made out of parts. Okay, so it's not a continuum when you go to the smallest, but there is a finite size. It doesn't get any smaller than that. And it's the existence of that finite size that changes the rules. That's exactly what changes the rules. So you cannot say, oh yes, this is not philosophy, I'm going to the infinitesimally small. No. You're going and you hit, as Dalia said, there is an atom. Nobody talks about half a hydrogen atom. That doesn't make sense. There is the hydrogen atom, boom. And now what is most amazing is that the same thing that you start to say, oh, no, come on, that's with matter. Well, it happens with energy as well. With energy, it's also, you cannot say, well, I have less and less and less energy. There is a point where you either have 0 or 1 unit. And that unit is called the photon. So, and that is what changes the rules, because our usual way of understanding the world, of predicting it with classical tools, is that everything goes all the way down to 0, but nature doesn't do that. And the price that we pay, as Dalia correctly said, is that we lose the intuition. We lose intuition. Because why? Because we're made of many, many atoms. And then when you go to the very, very, very small, you cannot go further, smaller and smaller. No. There is a building block. Nobody can think about a half a hydrogen atom. It doesn't make sense. A half no, it's not called a hydrogen atom. But also happens with energy. And so it's these, then, for example, in the PhD that Dalia did, she was very careful about working with 1 unit of energy and 1 unit of matter, okay? At the very limit, because if she goes further down, then it doesn't work, right? And so understand, this is the minimum that we have. And so in our quest for better technologies, well, you cannot work with half a hydrogen atom. You have to learn to work with 1. Okay. You cannot work with half a photon. You have to learn to work with 1. And that's where quantum technologies are very, very interesting. And we are harnessing them now. So
and that's why I had the pleasure of visiting you at your labs at University of Maryland. And you were explaining me this, impressive, a whole room just in order to freeze 1 atom and through laser, and that's the way you study it. And I understand, Dalia, that that was a lot of your research for your PhD.
Yeah, so you can prep a single atom, but in my particular experiment, we prep about, I don't know, 50,000 atoms. So we had like a small cloud of rubidium atoms inside a vacuum chamber. And the way that we can do this is using lasers and magnetic fields to first cool down the atoms and then trap them. And that's the initial step to study these systems. And then we use another set of lasers and we change other magnetic fields to, now that they are cold, we can, manipulate them and do whatever we want with them and study more carefully this system or exploiting this system.
How they react to different things.
Yeah, and the beauty is that, cold atoms, it's a very clean system because it's in a vacuum chamber, it's isolated, atoms are the same, if you're here or in China or in Mexico. So we know very well how they are going to behave if we, if we shine this laser or if we put this magnetic field. And yeah, I mean, it's really satisfying seeing how, you expect something to work and, and see it in the computer when you see your results after your measurements. But
you cannot see an atom, can you?
You can. And you need some instruments, lenses, camera, specialized lenses. You can see the fluorescence of an atom, but yeah, I guess you cannot see the internal structure.
Okay.
Let me just say, you can, right?
Okay.
Well,
yeah, you see something, of course.
If you do electron scattering or if you do X-ray scattering, you can. So, look, one of the things that is very important about quantum physics is that quantum physics has taught us that it's crucial to understand which question you're asking of the instrument you're studying. So, because nature always answers the question you're asking, but we, the scientists, don't always know which question we're asking.
What to ask, yes.
Okay. And so nature, because people, probably you have heard, oh, come on, the quantum physics says that light is a particle or that light is a wave. No, light is light. And the question that you ask gets answered as a wave or as a particle. Matter is matter. And the question that you ask is answered as a matter or as a wave, as a particle or as a wave. So, and all those, and this fact is one of the facts that gives you, enables many new possibilities that are not available in our larger dimensions, where it really doesn't matter very much what question you're asking, because you're not going to affect. If I asked you, does measuring the temperature on your room change the temperature of the room? The answer is no, right? But in quantum mechanics, when you are talking about an atom, measuring its energy or measuring its other internal property, it can affect it. You will send it into a completely different way. And then, of course, there are other things that the structure of quantum mechanics has brought in. The structure of quantum mechanics is a mathematical formalism that tells us how these minimal parts work. And that is where we realized that things like having a defined state, whether the cat is alive or the cat is dead, is nonsense. You have to say the cat is both alive and dead. Of course, the cat is got to be very, very small, right? And that's very, very important. And that is what will enable lots of things. This is the technically we call it the principle of superposition. And Dalia has used some of these things for some very, very beautiful experiments. So you should tell us, Dalia, right?
Yes, Dalia, tell us more about it and how quantum theory will be used for quantum computing, and what does that mean? Because sometimes I understand freezing the atom and studying it. I don't understand why does that have to do with my cell phone, or why is that going to be so important in terms of quantum computing?
So I didn't specialize in quantum computing, but basically the idea is using, like in classical, classical computers use bits, right? Where a bit can be a 0 or a 1, but and that's it. But then in quantum, because quantum in the quantum world works different, an atom or a photon can be a qubit, but because of the principle of superposition, like Luis said, it can be 0 and 1 at the same time, or an infinite combination of those numbers. And this property of quantum particles can help, in principle, to do some operations that it will take millions of years, even in the, or thousands of years in even the more powerful supercomputers. And if you have enough qubits in a quantum computer, it can take, seconds, for example. But, we're still in the process of developing powerful enough quantum computers. What I did in my research, it was more to do how we can connect two quantum computers, or how can we send quantum information to one place, from one place to another, because that's also different in quantum physics. In the world of quantum, you cannot just copy one quantum state and transport it to another place. So there's a complicated, it is more complicated than that. So I specialize more on how can we, transport quantum information, and it can be done with photons, and that's what I was trying to do.
And succeeded.
I succeeded in making a photon, but then, and partially interconnected with another quantum system.
In another building.
In another building, yes. So it's.
One question. I read a lot and hear a lot about nanotechnology, and that has to do with very little things. But it seems that yours is even smaller, the atom. But does quantum theory have to do a little bit nurtures nanotechnology?
Look, the typical size in a crystal between two atoms is about 0.1 nanometers. So so the nanotechnology is really dealing at the atomic level. Okay. So yes, there are things, because if you are talking about 1 nanometer, you are talking about 5 or 6 atoms. So yes, it has a lot to do. And the advantage of nanotechnology, of course, is as its name says, it's very small. So you can pack lots of things in a very small volume or area. And a lot of the pursuits of how to build a quantum quantum computers, some of them are going through the path of nanotechnologies, right? And in particular, to try to direct or manipulate the light. You could try to do all that in an extremely small area, right? The computers are still, they tend to be bulky, right, Dalia? Even the ones that are successful in doing simple operations, they are not yet the size of your cell phone, Alberto. They are pretty large.
But what the reason why companies like Google and IBM are so interested in this research and development of quantum computers is precisely because of what you were saying, Dalia, the speed that will allow to have access to more information, kind of like the 5G thing now, but applied in huge to computers. Is that all right? Did I understand?
One very, very important thing. The advantage is not in how fast you do the operation. Okay? The operation, let's say, will take a certain amount of time. But the advantage that quantum computer gives you, which is crucial, is that you can use different algorithms that you cannot use classically. So, in other words, this is maybe too simplistic, but not too wrong. Instead of first having to do suppose that you have to do 100 sums to get to the result. And quantum algorithm allows you to make in one operation those 100 sums. So if each operation takes you 1 nanosecond, in a classical computer that will take you 100 nanoseconds, in a quantum it will take you 1. Now let's talk about 1,000,000 operations, and now you can start to see that if you can do it in parallel, but that's the algorithm. It's not like 5G. No, 5G is the speed of the operation. It's the algorithm. It's how do you do what you do to calculate. That's where the big gain is, and that's where Google and IBM, and of course, all the Chinese companies that will win, right, are very, very interested.
Great. Now, Luis, tell us a little bit about your experience with your students, with your Chinese students that you've been going in the last several years.
No, I have had
the money that the Chinese government is putting in the labs.
So I have been going to China for quite a few summers to spend time with some of my former students and associates. And let me just point out to one institution. It's the University of Science and Technology in Hefei in China. That used to be the University of the National Academy of Sciences, and it used to be in Beijing. And when the things got very hot between the Soviet Union and China, China decided to take the university out of Beijing in case it was bombed. So in the 1960s, they moved the university to Hefei, and it is, they claim, it's the MIT of China, right? And it really is very, very, very impressive. To put it in perspective, the United States decided to put $1 billion into quantum research for 5 years. The state of Anhui, where Hefei is, decided to put $2 billion on that state.
Not the country, yeah.
No, $2 billion.
Wow.
So when you go to the university, it's just a dream. And these are the guys who have done things with satellites and measured things with satellites for quantum communication and quantum protocols, quantum algorithms. They do it in outer space. Why? They have the resources.
Yeah. Wow.
And on the other hand, they have a lot of let's call it the number of startup companies around the university is as impressive as it is in Cambridge, Massachusetts.
Wow. So we will be seeing in the next years a lot more Chinese science, applied science done.
Oh yeah. Yes. No, they have it very, very clear.
And is there a comparison with India or no? Okay. So the big players is the US and China.
It's China.
Okay. Now, Dalia, as we've heard, Luis is very bright and very wise, but he is a relativist. And it has to do with, I suppose, because of what he says, because of his how physics has nurtured his way of thinking. Has physics been important in shaping your beliefs and your way of seeing the world, Dalia?
Quantum physics, you mean? Has
Physics.
Physics. Oh, yeah, definitely. Definitely. I mean, in the professional part, it can be frustrating, honestly, sometimes, in an experiment, like my lab is, in the back. And there are so many elements that can go wrong. So, but then, you're patient, and then you start to figure out and debugging. And then when everything works, it's very satisfying. On the other hand, also being a scientist makes you skeptical about things and makes you to ask questions, in every aspect of your life. And I think that's also very important, right? When you navigate through life, when you decide, when you go to vote or when you go to the doctor, you have to ask questions. I don't know. I think being skeptical has been a very important skill that studying physics has taught me. I will think that's the most useful.
It's a lovely contribution. I agree. In my case, when I've been more skeptical, for example, of love, it's when I found it. So sometimes it happens. So why don't you both have a closing thing to tell us about physics, the world? How has the pandemic affected your way of working? Has it taught quantum physics something, living in this pandemic?
I don't know, Luis, you want to start? I have to think about it.
Look, fortunately, I have had the fortune of having collaborators in different parts of the world, which have fared much better, meaning China, than currently both Mexico and the United States. So I have been able to continue collaborating with them. We meet, we discuss results. I ask them to do other measurements. It's been very challenging to direct or help direct students in a lab from Washington when the lab is in Vancouver. That I can tell you, because using Zoom or Skype is very different than being in the lab. And I'm pretty sure Dalia will agree that there's nothing like, okay, this way is the way you turn the thing. And that's been challenging, right? But this pandemia has also given me the opportunity to give some classes in Mexico, right? So I've been giving classes in San Luis Potosí. So, sorry, Dalia. One of my former students is professor in San Luis Potosí. So, hey, would you like to teach quantum optics? And so I've been teaching quantum optics too. Yeah.
So, what about you, Dalia?
Well, part of the pandemic, since it started...
You moved to Boston before the pandemic, so you, 1 month before, so you arrived to a closed city. It must have been difficult, no?
It was definitely difficult. I mean, it has had bad things and not too bad things for me. Like when the pandemic started, like I started to write my thesis. So it was like a good timing, so I could just sit day and part of the night to write and finish, because otherwise I will be too tempted to work inside the lab and not write my thesis, because every good, any excuse is a good excuse to not write your thesis. So I didn't have one, so I finished on time. Luis can tell. It was a little bit isolating. One of the good things was that when I defended my thesis, it gave the opportunity for friends and family in Mexico, to share this moment with me that otherwise wouldn't be possible, right? So I really appreciated all that support, even if it was in Zoom. But also the communication with, now that I'm in Boston too, and I help the younger students in my lab, and sometimes I wish I could be there and explain them how to do things, but it's surprising that the level of communication you can have. So it hasn't been too bad. It has taught me to see the silver linings and kind of be optimistic.
That's good to hear. Well, thank you both for wishing to share with us your experience. I'm sure that many like me are now more interested in understanding first the important contribution that you physicists give to the world in doing that research, and to try to understand that micro world that makes us be the way we are. Thank you so much.
Thank you very much.
Thank you.